All right. I'm glad you guys could be here today. It's good to see you all. Clearly, I'm bored, so I've set up camera equipment because, well, as you know, I'm kind of in love with myself, so I figure, this way, you know, if I can't actually be there, you should be forced to have to see me. And yes, I know. I haven't shaved. That's okay. I'm not coming to school right now, so I can just go more mountain man look. It's okay. Eventually, I'll shave again. I'm glad you guys could all be here today. I want to talk a little bit about what's happening over the next couple of days. First, uh, I posted a humbling question. I think everybody should attempt it. Look, we're in review now, and yeah, the workload's going to be high. You need to live up to that. The humbling question is extra credit, and you're going to need it. So I would encourage you to take a look at it. These are questions that have what I feel are really, they're kind of challenging. They don't happen very often, but either it's mathematically or hard to conceptualize. The next couple you're going to see have some pretty heavy calculus. These are charge distributions related to electric fields and electric potential. So take a look at the one I posted today. Try and turn it in today. Um, our discussion today is going to be relatively quick, but I have asked that you also submit something separate for homework besides the FRQ I'm going to post. And that is, you should submit to me the derivation of the three basic capacitors. Now, there are three. There's the parallel plate, there's the coaxial or cylindrical capacitor, and then there's the spherical. I'm going to run through how to do the parallel plate capacitor. And to do that, I want to remind you that the parallel plate capacitor is the one that has two infinite sheets. I want to go through the process, and then if there's time, and it probably won't be, I'm going to talk a little bit about dielectrics, but that might have to wait. Now, my plan tomorrow is to surprise you with a full FRQ test. You're in a position now where we would have already done this if I'd been there. I don't want to wait any longer. So if you're watching this video, you now know what the surprise is going to be. If you're not watching the video and just running out and doing the FRQs, well, we're going to catch you tomorrow. It will be a full test from a specific year, and it will be treated as a test. The sub will have instructions, and it should be printed out before you get there to make sure you guys have the maximum amount of time. I know it's a Thursday, so you'll have to hurry. So it's possible I will leave out one part of one FRQ, but you'll have very close to 45 minutes. Either way, that's what's happening tomorrow. So without further ado, let's talk about what's happening today. We're going to be doing a derivation of the parallel plate capacitor with a quick reminder of what capacitance is actually about. I don't really think I need to do RC circuits with this again. I think we got a pretty good handle on it. If you believe I'm wrong, you should send me a message letting me know, no, I need to do a review on it. But I kind of feel like we should focus on the dielectric problems and maybe a few other little things that we didn't talk a lot about, like the construction of resistors, charge density, some stuff that we kind of breezed over. The stuff's not super critical, but definitely construction of a resistor and how we get the resistor design, I think we should probably talk about. So let's talk about capacitance first and foremost. A capacitor is any two chunks of metal. Anytime you have two chunks of metal, there's the possibility that you could store energy by moving charge from one metal to the next. So when we connect a wire there and place a potential difference between them, we could move charges from one to the other, creating a charge differential. This establishes the creation of an electric field, and this electric field will store energy. Now, a capacitor like this it's random. And like I said, any two isolated pieces of metal could be a capacitor if you want them to. There's no way to predict the size of this capacitance, but you could measure the size of the capacitance. I'll remind you, capacitance is defined as the amount of charge you separate per an applied potential difference. So when I apply a potential difference, I probably should put the little potential difference symbol there. When I apply a potential difference, how much charge is pushed from one to the other determines the capacitance. It's the capacity to hold or store charge. So if you have different groups of metals, you could compare them by capacitance by applying the same potential difference to each pair and seeing which one holds more charge. What you couldn't do is, for some random two pieces of metal, attempt to predict the capacitance based on the geometry. There's no easy way to find how much electric field is created due to the charge if your object doesn't have any kind of regular or easy to predict shape. But what we have found is that for some kinds of regular and repeating shapes, you can find the predicted capacitance for those shapes. That brings us to the parallel plate capacitor, the cylindrical capacitor, and the spherical capacitor. So before I go into that, just a quick reminder about units. Let's spend more time, not less, dealing with units. A volt is a joule per coulomb. Just a reminder about that too. Remember, a volt has in it work, but it's work per unit charge, so joule per coulomb. And yesterday, I should have done a quick thing about what electric fields are. Newtons per coulomb for sure, but also volts per meter. These are two different ways to measure or use units for the electric field. The capacitance is coulombs per volt. Interesting, maybe, perhaps, I don't know. We've called that the farad, and we all know now that a farad is actually a large amount of capacitance. But I always find it a little bit interesting that when you start really digging down, these things become pretty complicated. Since capacitance is coulomb per volt, that's a coulomb per joule per coulomb, which is coulomb squared per joule, but a joule is a Newton meter, but a Newton is a kilogram meter per second squared. So that makes that all of those things, or coulomb squared second squared per kilogram meter squared. Bizarre. You know what's really bizarre about that? The denominator, same unit as the moment of inertia. Just a coincidence. But wow, that's a lot, isn't it? It's not like I can see the ability to store charge in that. I can't see it. But that's in the MKSC system for units, that's what it is. Crazy. All right, let's get to the heart of our discussion today, because I don't want to waste your time, but I also know that I have a tendency to be long-winded. And today I should finish up with time for you to start your FRQ. Sorry, I got something in my eye. So let's start with a reminder. If we wish to predict the capacitance of two pieces of metal, first, we need a way of expressing the electric field for every location in space for those two pieces of metal, or between those two pieces of metal. That's what we're looking for. The electric field that fills the space between the two pieces of metal. Now, if it's random or non-symmetric or unable to be measured, you can't do that. We are looking for an expression. E is a function of location or something like that, so that we can eventually do the second part, which is to find the potential difference from one piece of metal to the other. Now, you can't really do step one. If you have two pieces of metal, there's no reason why there's an electric field there. In order for there to be an electric field there, those two pieces have to be charged, and for those two pieces to be charged, you have to apply a potential difference to move those charges. Well, if you know what the potential difference is, then why are we doing this process? Well, it's a little bit different than that. What we're going to do is we're going to say, well, what is the electric field that fills the space between the two pieces of metal for a given charge. Meaning we're going to assume there is a charge there and use this charge to figure out what the potential would have needed to have been to push those charges there. That's what we're really doing. And that leads us to 3, our ability to determine the capacitance by doing this quotient. In practice, what it usually means is using something like Gauss's law or something like K dq over r squared to figure out the electric field. None of the ones we are going to do use this to figure out the electric field. They all use Gauss's law. So let's do the parallel plate. To do the parallel plate, what I'm actually going to do is do a single plate by itself first. Here's my single plate in space by itself. And I want to look at that plate 2 different ways. Let's look at it from the top and look at it from the side. And let's remember that we want to find the electric field for a charged plate. To be able to do this, we're going to take some liberties with our mathematics and the universe. First, we're going to treat this plate like it's really, really big compared to how far away we're measuring the electric field. Meaning, we're going to measure the electric field just a small distance away from the top of the center of the plate. This allows us to make the assessment that our plate is infinite. Now, I know we could use the expression for the electric field near an infinite plate of charge, and you should all have this memorized. In fact, you should have the electric field for a line of charge memorized and the electric field for a point charge memorized. And I know you have this one memorized, but you should have them all. But I'm going to do the due diligence and assume that maybe we don't know it. Now, on the exam, if you know this, unless they ask for you to prove it, don't. Just use it. But I'm going to assume you don't remember how to do it. So to find it, we need to, of course, use Gauss's law. I'm going to assume that the plate has area A and the total charge is Q on the plate. This means I have a charge density of Q over A for the plate. For Gauss's law to work, I'm going to use a cylinder. And this cylinder is going to be located near the center of the object, but it cuts the cylinder, and half of the cylinder is on the top and half the cylinder is on the bottom. So my cylinder from this vantage point will look like this. Let's see. There. And half of the height of the cylinder is above and half of the height of the cylinder is below. So my cylinder has a radius of r, and therefore the area of the top of the cylinder is pi r squared. All right? Any questions about those choices? Not like you can ask them. So I'll just act like you don't have any questions and plod on. There is a certain amount of freedom and liberty in not having to see if you have any questions. I keep wondering what Aramis is doing in class. Is he really watching is he just slowing him down and backing him up? Is he asking Lawrence what the answers are? Or better yet, is he saving them all up for when I get back? Of course, I wish my superpower was right now. This is not the one I put in the envelope. I'd say like super antibodies. That would be my superpower right now. But no, that's not the one I put in the envelope. All right, so Gauss's law. Q enclosed. Sorry, I hit a button. Gotta stop doing that. Q enclosed equals epsilon naught times E dot dA. It's Gauss's law. Somebody in tutoring last night asked me how you calculate flux. All flux is calculated the same way. It is the integral of a field times an area, or the sum of the field that goes through an area. Gauss's law is special. That's why the circles on the integral don't get it confused. We've had other flux computations, but those generally have just been a simple integral, like we have some for magnetic flux. We didn't do the circle because we weren't doing it over a closed and bounded surface. The circle here is to remind us that Gauss's law must take into account a closed and bounded surface, so that basically it has to be watertight, this kind of surface. It's a full volume and nothing gets in or out. And we are adding up all of the electric field that would pass through that volume. We have a cylinder here. So let's do the right side of this first, because I don't know, I want to. I'm going to break up my cylinder into three parts: the top, the bottom, and the sides. And I'm going to recognize that should this be a uniform sheet of charge, the electric field should be uniform, top and bottom, like so. That's what I expect from my electric field, which tells me that I can break up my integral into three parts. The integral for the sides, E dot dA, plus the integral for the top, E dot dA, plus the integral for the bottom, E dot dA. Now, let's be clear. For there to be a flux, electric field has to pass through the area. Remember the direction, there's a dot product here. That dot product refers to the cosine between the electric field and the direction of the area, and the direction of the area is perpendicular to the surface. So I get electric field passing through the top, I get electric field passing through the bottom, I get no electric field passing through the sides. Also, as long as my cylinder is centered and is symmetrically placed, then the electric field that passes through the top and the bottom should be uniform as well. And what I mean by that is, I believe I can state that in both cases, the electric field is constant, and all I'm doing is adding up the area of the top, and in this case, adding up the area of the bottom. And I believe, since I've centered my cylinder, the size of the electric field for the top is the same as the size of the electric field for the bottom, so those two E's are the same, which allows me to go one step further, which is say that this is going to be E times times pi r squared plus E times pi r squared, giving me the total flux, including my constant, 2 epsilon E pi r squared. That represents the right side. Let's deal with the left side, Q enclosed. Q enclosed is going to be sigma times the area enclosed. That's how much area is being cookie cuttered out of my sheet. Right? This cylinder kind of cuts through the sheet and cuts away a certain amount of the sheet. That's like a cookie cutter. And I think we can all agree the area enclosed in this case is going to have to be pi r squared. And in addition to that, sigma in this case, total charge divided by total area of the sheet. So we can bring all that together. And we get Q over A times pi r squared equals 2 epsilon naught E pi r squared. And clearly the pi r squareds go away. Solving that for E, I get the obvious answer. E equals Q over 2 epsilon naught A, which is the same as this, except the sigma has been replaced with Q over A. All right, almost there. I want to find capacitance. So now we have found the structure of the electric field near the shape of the two pieces of metal I'm going to use. And the two pieces of metal I'm going to use are, again, trapezoids. Not trapezoids, sheets, something like that. So I need two of them. So there's two of them. Let's place them so that they are in a reasonable arrangement. So there we go. So area, separation distance, and let's go ahead and do what we said, and that is charge them so they have a charge Q. That's going to make this one have a charge negative Q. All right, so negative Q and positive Q. Now, what I need is an expression for the electric field that must exist between the plates. And by the way, that electric field should be, or you can't see that, the electric field should be this way. But let's consider this. I have two sheets here. So the top sheet is producing an electric field equal to Q over 2 epsilon naught A, and it is directed downwards. And the bottom sheet is also creating an electric field of Q over 2 epsilon naught A. When I say downwards, I'm focusing on what's happening between these two sheets. I know that there's an electric field upwards from the top sheet, but that's being countered by the downward electric field from the bottom sheet. So these two cancel out outside. And if you don't believe me, put a Gaussian surface that extends from the top of the top sheet through to the bottom of the bottom sheet, and it would enclose no charge. So the electric field outside of this capacitor should be zero. But what I also want to recognize is that we get twice the amount of electric field between the two plates of the capacitor. So take those two, add them together, and the electric field between the plates of the capacitor, in this case, is going to be Q over epsilon naught times A, where A represents the area of the plates. So we now have an expression for the electric field between the two pieces of metal. It's a constant because it's a sheet of charge, but it's still the electric field between the two plates. So when I go back to where I started here, I have done part one. I have found the electric field that fills the space between the two pieces of metal for a given amount of charge Q, and more importantly, this value is uniform between all the metals. So now let's go to part two, find the potential difference from one piece to the other. That part's pretty easy. And yes, I'm throwing away the negative sign. Why? Because it doesn't matter in this case. We know the direction the charges have to be driven. Finding out whether that potential is positive or negative doesn't matter. We will establish that the potential difference we're going to use is one in which the upper side of the potential difference is connected to the positive charge. So I just need to know what the value of this potential difference is. For this case, I'm going to use the bottom one as I'll put the negative sign there. I'll use the bottom one as my zero, and I'll go the other direction. That way, I put the negative sign in it because I realize if I don't do that, somebody's going to screw this up, and I don't want that to be screwed up. So there's negative sign. Let's go ahead and do this from 0 to D, my electric field Q over epsilon naught A dot ds. In this case, I'm going against the field. So I'm going upwards, but the field's against me, so that dot product that's right there produces the cosine of 180. So cancels out the negative sign, bring out my Q epsilon naught A, and I'm taking the integral of ds from 0 to d, which, lo and behold, gives me, not a surprise, QD over epsilon naught A. This is my potential difference between the plates. Thus, step 2 completed. Goody. Feeling like a boss now. So, onward to step 3. Step 3 is the easiest part of this. Capacitance equals Q over potential difference. If you've done this correctly, what you will be left with will have nothing in it that has any residual reference to charge. And everything that's there should be geometric. So for us, that'll be Q over QD over epsilon naught A. Do a little bit of math. Q epsilon naught A over QD, and that means C equals epsilon naught A over D. Ta-da. Not a big deal. We know the answer of this, and you should already know the answers to all of them. You should have them in your notes. What you should do is go through the process of rewriting them. I want you to do that. I want you to do this for each of the 3. I've just gone through it with one. If you've been taking notes while you've been watching the video, then you have 1/3 of the assignment done. If you haven't been taking notes, well, phooey on you. You should have been. Briefly, what I want you to consider is that, remember, the infinite line of charge has charge density, lambda, which would be charge per unit length. You need an expression for the electric field around this infinite line of charge. That's how you're going to have to do the coaxial one, because the coaxial cable, remember, is one that's going to have, the coaxial capacitor has an exterior cylinder and perhaps an interior cylinder, and you will be charging the exterior maybe negative Q and the interior positive Q. Usually a cylindrical capacitor has a fixed length, so the lambda is going to be Q over L. You will need to determine what the electric field is around an infinite length of charge. Gauss's law will help you with that. I would use a Gauss's law shape that is a cylinder again. Now remember, when you work this one out, you get an inverse relationship, meaning the electric field is proportional to 1 over R. I don't want to give it away. You should remember how to do it. I'm saying that because when you go to find the electric potential here, it is likely your answer will have the natural log in it, with probably something like the inner radius and outer radius here. That one's kind of funky when it comes to calculating the capacitance. Spherical capacitors, well, yeah, it's a sphere. It's pretty easy. It's a point charge and then a sphere around it. Pretty sure you can do that one. So you guys do those, write them up. They should be in your notes. Do not take a picture of your notes and say, here you go, Mr. Shelton. Please take the 5 minutes to at least rewrite them out. And if you can't find them in your notes, they are both in the book, explicitly and detailed, laid out for you. So you can just crack open the book. It'll probably make a noise if you have an actual book, because you've probably never done it before. So consider doing it that way if you're concerned about it. All right, one last thing, and that is dielectrics. In all of these, remember, we've been dealing with using epsilon naught, because epsilon naught is, for all intents and purposes, the way an electric field gets established in space. But most of the time we are not in space. Our capacitors have at least minimum air between them. It's hard to have a vacuum between them, but almost always instead we have a material that fills the space, and this material has a different dielectric constant, epsilon. So we usually or generally consider that the dielectric constant, kappa, is some value times the dielectric for free space that gives you the dielectric of your material. And we call this the dielectric constant. It's almost always a value greater than 1, which means most materials enhance or increase the ability of two pieces of metal to store a charge. And this is because when you start putting an electric field in there, most materials will enhance that electric field by lining up with the electric field. Kind of cool. But what this ultimately does is it changes our calculation by putting kappa epsilon naught A over D. Or if you haven't figured this out, just kappa times C for vacuum. Now, this doesn't, I wouldn't put that to memory here too much, but that's what, the way you could think of it. But this is generally what we put, that there's going to be some value there. This is important because we do have a series of kinds of questions where systems of capacitors get charged, and then we manipulate the dielectric by either taking the dielectric out or putting the dielectric in. You should go through a couple of practice scenarios, and I can think of 4 practice scenarios you should look at. The first practice scenario is 2 capacitors in series with a applied potential difference that stays there, and you place a dielectric between the plates and see what happens. Questions like, does it store more energy or less energy? Does it draw more charge out of the battery or push charge into the battery? Those are questions you should answer for this case. You should do it for the charged system after the potential difference has been removed. You should repeat this now for a parallel set of capacitors. Again, one in which the potential difference remains in place and the dielectric is put in place, and for one in which the potential difference is removed after the capacitors are charged and the dielectric is added. It's not a big deal to say this, but I'll say it anyways. Consider also you should repeat this for when the dielectric is already there in place and is then removed after the system has been charged. You should do all of these. As a reminder, the thing to remember, and this is probably the whole crux of why you should repeat this or why you should do this, is that capacitors in series have to have the same amount of charge on them. So when you add the dielectric, you can't suddenly make them have different amounts of charge. Charge will change until they have the same amount of charge. That has to be true whether they are in series with a potential difference or in series without a potential difference. Okay? Capacitors in parallel, they don't have to have the same amount of charge, but they do have to have the same potential difference. That's true whether there's an applied potential difference or not. They have to have the same potential difference. And remember, if you remove, let's get all this distraction out of the way. If you charge up this system and then remove the potential difference, this suddenly does not become 2 capacitors that are in series. Capacitors that are in series and have been charged will have opposing charges with their plates like that. Capacitors in parallel that have been charged will be prevented from having those charges return even though they're looped together because they're both raised to a higher potential. So there's nothing to allow these charges to move back and forth between those 2 plates. Not unless you introduce something that has the potential to change the electric potential between the plates, like a dielectric. So, in the closing minutes of class, because I'm looking at the timer here and it looks like I've been talking for a while, let's say you have two equivalent capacitors. Let's go just 2 farad capacitor, and you have a 4-volt power supply. Try the series circuit, and let's say you have a slab of dielectric material with a dielectric constant of 3. Put it together, make a series circuit, find all the charges, find all the potentials, and then add the dielectric. We're going to pick this up the next time we hang out. So hopefully it'll be live on Monday, but perhaps if things don't go well, it'll be this on Monday, which is no fun. Have a great day. Talk to you all soon. And look forward to being back in school. Just hanging out here in my porch. Less than fun. Really, less than fun.